The content of today's lectures recap: stability analysis of explicit scheme, stability analysis of implicit scheme. So till now we have considered the discretization of derivatives, how we obtained them from Taylor series, what are the different errors, what are the basic definitions, consistency, stability, and convergence. So now we will see how we can apply the von Neumann theory to 1D linear advection equations. So stability analysis of explicit schemes. If UIN is the exact solution of a discretized equations, so first we discretize our equations, and if we can get the exact solution of that discretized equations without any round off error, and let us say it is ui bar n, and uin is the numerical solution of the discretized equations, which includes round off errors and boundary condition errors and discretization errors, etc. And n is the numerical scheme and d is the differential equation. So we can calculate our error as uin, which is the exact solution, will be equal to the numerical solutions of the discretized equations plus error. So we can see that this is only valid for linear equations, and we can prove that for the linear equations the error terms epsilon in will satisfy the difference equation. So from the previous notes that error satisfies the difference equations, we can simply put the error terms in our discretized form of equations. So let us say we have linear convection equation del u by del t plus del u by del x equals to 0, where c is the speed of propagation of property or speed of convection. So let us discretize the time derivative terms with a finite difference version and space derivative terms with a central difference approximations. So we will get uin plus 1 minus uin over del t plus c twice del x ui plus 1 n minus ui minus 1 n equals to 0. So this is the difference equations, and our objective is to calculate the future value of u at every node. Uin plus 1 is the future value. So our algorithm will become uin plus 1 equals to other terms. So in explicit schemes there is only one unknown, and this unknown is expressed in the form of other known terms. So we can simply calculate our unknown terms, which is the value of u at some future level. And here sigma is defined as c delta t by del x, which is CFL number, which is called Courant-Frederick-Lewis number, upon which some stability criterion is built, and thus it poses a restraint or constraint on time step. So from von Neumann stability analysis theory, we can replace all the u terms with some error terms, and the generic expression for the error in the form of v n plus k e I bracket I plus m phi. Phi is phase and capital I is under root minus 1 and capital V is amplitude. And k and m is any integer. So if you put that generic error form in our difference equations, then we can get Vn plus 1 Ei I phi equals to Vn Ei phi minus sigma by 2 V n e to the power I plus 1 phi minus Vn Ei I minus 1 phi. Where V is the amplitude and Vn plus 1 is the amplitude at the next time level. So we can calculate our magnification factors as Vn plus 1 upon Vn at any node, and this must not be greater than 1. If it is greater than 1, the error will grow in time and our solution will become unstable. So divide this above equation by Ei phi, we will get this. So finally we will get the amplification factor G in the form of sigma and sine phi. So just by manipulating it, we can see that this will be always greater than 1. So the amplification factor's magnitude will always be greater than 1. So we can say that error will always grow irrespective of the time step and mesh size. Hence, the finite difference in time and central difference in space strategy for one-dimensional linear convection equation is unconditionally unstable. Now let us look at another example of an explicit scheme. Remember that in explicit schemes, all the known terms are kept at right hand side and all the unknown terms which we want to calculate are kept at left hand side. So implying the forward difference in time and now the backward difference, which is called upwind scheme, we will discuss it later on. So the backward difference in space will give this formulation and algorithm. Now again doing the same exercise, replacing u with error terms, and for the error terms we can put the generic error solution in the form of amplitude. So after some algebraic manipulation, so we will get the magnification factor G in the form of sigma, that is CFL number. So again playing with some trigonometry, we can replace the 1 minus cos A, 1 minus cos phi terms after taking common sigma, and now our G will be 1 minus twice sigma sine square phi by 2 minus I sigma sine phi. So separating the real and imaginary part, the real part of the amplification factors will be 1 minus sigma plus sigma cos phi, and imaginary part will be minus sigma sine phi. So if you plot in a complex plane G, then it will look like the small circle, and the big circle is a unity circle, which is a criteria for stability. So beyond this, the unstable region, and inside this is a stable region. See, if our small circle or the G should lies within the unit circle. So if you see that the G in the complex plane is a circle with a center at 1 minus sigma and with a radius of sigma. So obviously sigma must not be greater than 1, which is the radius of the unit circle, to completely lie inside the unit circles and to ensure the stability. So there are another methods which require some more algebraic manipulations, where you can calculate the constraint on sigma so that it is inside the unit circle region. So for the value of sigma less than 1 and greater than 1, our strategy of upwind difference, means backward difference in space, will be conditionally stable. Now we will take a look at the stability analysis of implicit scheme. So in implicit schemes, there are more than one unknown and the many quantities are expressed in the form of future time level. So let us discretize the implicit backward difference in time and backward difference in space. So after some algebraic manipulation, you will get this. Ui n plus 1 equals to ui n minus sigma ui n plus 1 minus ui minus 1 n plus 1. So there are many terms which are at future level and only one term which is known. So we have discussed in a previous lecture about how to solve these type of equations, in which we have to write this equation at all the nodes and then solve them simultaneously using Cramer rules, using Gauss-Seidel iterations, etc. So the amplification factor G can be written after some algebraic manipulation as 1 over 1 upon 1 plus sigma 1 minus e to the power minus I phi. So the magnitude of this amplification factor will be 1 over 1 minus sigma plus sigma cos phi whole square plus sigma square sin square phi. So this will always be greater than less than 1. So because the denominator will always be greater than 1. Hence the backward difference in time and backward difference in a space for an implicit scheme is unconditionally stable. Summary. So stability conditions place a limit on the time step for a given spatial step, because sigma, which is CFL number, is equal to C delta T upon del X. So if there is a mesh size of 0.1 and if C is 1, so we cannot choose our time step large in case of explicit formulation. Implicit schemes have no limit on time step because there are no stability condition posed by von Neumann stability analysis on sigma or the Coulomb number. So we can choose the time step as much as we want. But we will not be able to we will not be able to gain the insight of transient flow conditions if we choose a large time step. However, in implicit schemes, we have to solve a large matrix. So if the number of nodes are greater, then the implicit schemes may have disadvantage in terms of computational time. So for example, if we have a 10 by 10 grid and if we have a 100 by 100 grid, so on a 10 by 10 grid, we have to solve 100 equations at a time, and on a 100 by 100 grid you have to solve a 10 to the power 4 equations simultaneously. So explicit schemes are very easy to code. They are straightforward because they are based on the time marching strategy, and we can calculate our solutions over a period of time by incrementing time step. It is still a debatable area which scheme or which strategy is better, implicit or explicit. For the diffusion equation, we can show that the explicit time step restriction is not too severe because of the numerical diffusion is very large uh, as along with the physical diffusion. So this stabilize the solutions and damn the oscillations which occurs during numerical computations. However, I would like to mention that all these stability theories are very well known and valid only for linear schemes. As far as the nonlinear schemes are concerned, there are no good theories which can perform analysis of the schemes, whether they will be stable or not. So in case of nonlinear equations, for example, Navier-Stokes equation, we have to rely on the number of simulations, and after the number of simulations we will arrive at the conclusion whether the scheme is stable or it is converging or not. Questions. So what is Courant number? So you can, it is a very basic question, you can find it. And another interesting question is, can we have a mix of implicit and explicit scheme? And if there is the third question is, if there is an unstable schemes, what are the method to stabilize it? So just search in the Google artificial dissipation and artificial viscosity. Thanks.